This is one of a series of lectures by the Further Maths Support Programme for revision of A-level mathematics. In this lecture we're looking at Edexcel Mechanics 1 and the topic is vectors. Now, vectors can crop up in a variety of different questions, but some basics first of all. You need to be able to calculate magnitude and direction of a vector. This is Pythagoras' theorem, so that we would look at x squared plus y squared, the components in the x and y direction square rooted for the magnitude of the vector. This may be a force or a velocity or anything which can be expressed as a vector. And the direction, usually using the x and y components, we'd work out the angle theta as being tan inverse of y over x. However, be aware that the direction is usually going to be in context, so we may be talking about bearings. We may want to express the direction relative to some other direction, so the questions can be a little bit more complex than simply calculating tan inverse of y over x. The applications, it says, to vectors to displacements, velocities, accelerations and forces. Forces in particular will come in, and we will be using Newton's second law, so F equals ma, where obviously force and acceleration are now vector quantities. It also mentions the idea that vectors may be set in terms of I and j components. It quite often be in context, so I and j may well be along the easterly axis and the northern axis if we're talking about something in bearings. So I and j are just the unit vectors, and they will be defined in each question. Other things that you might need to look at are the use of change in displacement divided by time for velocity, and change in velocity over time for acceleration. So all of these are covered in other parts of the specification. Here we're just looking at them specifically in terms of using vectors. Alright, having said that, then we'll look at one or two questions which hopefully will illustrate these points. The first question comes from the June 2010 paper. In this one we're given the fact that a particle is moving with some constant velocity negative 3I plus 2j. So if we try and illustrate that, it's moving with some sort of velocity like this, negative 3I plus 2j. And at time t equals 6, it's at some point with position vector negative 4I minus 7j. So it's at some position here where we know its position is negative 4I minus 7j. Now let's try and illustrate roughly where that is in relation to the origin. And we want to know at what point it was at 2 seconds, at t equals 2 seconds. This is t equal to 6 that we've got here. And then to find the distance of p from the origin. So the first thing to do is to try and calculate the position that it was at when t was equal to 2, given that it's been moving along in this direction for 4 seconds. Now you don't actually need to draw a diagram. You could go straight into the idea of algebra. So let me look at it in terms of the algebra. We could say that the change in the position vector so the change in the displacement divided by time is equal to the velocity. So that tells us that negative 4I minus 7j minus that position vector at time 2, let's call that R1, its first position, is equal to 4 multiplied by the velocity, and the velocity is negative 3I plus 2j. So now we need to solve that equation for R1. So R1 is equal to negative 4I minus 7j minus 4 times negative 3I plus 2j. And that turns out to be 8I minus 15j. So let's just look at that on the diagram here. What we said is that in this diagram, the change in position, that was R2 minus R1, is equal to 4 times the velocity v, because we're acting along here for 4 seconds. Now the question asks not for the actual vector, but the distance of p from the origin. Now that's just a matter of working out the magnitude of the displacement now. The distance from p, the distance from O at t is equal to 2 is then the magnitude of this, which is root of 8 squared plus negative 15 squared. And if you calculate that, it turns out to be 17, and the question is talking about distances in meters, so the distance is 17 meters. The allocation of marks here was firstly getting a correct equation, so M1 for the method and A1 for the a correct equation. Following that through and calculating the value of the vector r, there's a further A1, and then a method mark for using the idea of the magnitude of the vector, followed by an A1 follow through. So had you not got the correct vector, you could still pick up both M1 and A1 if you'd calculated the correct magnitude of the vector that you had found. The second question I want to look at comes from the January 2011 paper. This one says that the particle of mass 2 kilograms is moving under the action of a constant force F newtons. The velocity of p is 2I minus 5j meters per second at time 0 and 7I plus 10j at time t equal to 5. So with that information, we first of all have to calculate the speed of p at time 0, the vector form f, so in the form ai plus bj, that's finding the value of f, the force which is producing the acceleration, and then the value of t when p is moving parallel to I. So taking those one at a time then, the first one is simply calculating the magnitude of a vector again. So in part A, we're asked to work out the magnitude of the speed. Well, we're told that the velocity is 2I minus 5j, so that the speed is simply the magnitude of the velocity at that time, which is Pythagoras' theorem, giving us a value of 2 squared plus negative 5 squared square rooted, which is root 29. No need to calculate it as a decimal, but you may if you wish. This is a speed, so meters per second. In the second part of the question, we're asked to find f. Now we haven't got the acceleration. We're going to have to use Newton's law here, so that f is equal to mass multiplied by acceleration, and that the acceleration is change in velocity. Let me do that as v2 minus v1 divided by time. So it's a two-stage question, this one. So starting off with the acceleration. The acceleration is equal to 1/5 of v2, that's 7I plus 10j, minus v1, 2I minus 5j. So first of all, calculating that, I leave the fifth outside the bracket. It's 1/5 of 5I plus 15j. Just be careful with the negative arithmetic there. And of course then that is equal to I plus 3j. Now that's the acceleration. We're actually asked for the force F, so we can use F equals ma. That's just the mass, which we're told is 2, so the force is 2 multiplied by the acceleration, and of course therefore that is 2I plus 6j. The final part of the question asks us for the value of t when p is moving parallel to I. So this is talking about the velocity of p, and we need to realize that we've got a velocity which is changing, so that we know the initial velocity u, which is 2I minus 5j, and we now know that the acceleration a is equal to I plus 3j. So we can use equations of motion. Remember, the equations of motion are really vector equations, so the Suvat equations, v equals u plus at. So the velocity at any given time, v, is 2I minus 5j, that's the initial velocity, plus the acceleration, I plus 3j, multiplied by time. Rearranging that so that we've got the I and the j components separately, the I component is 2 plus t, and the j component is 3t minus 5. Now all sorts of things could be asked about this now. When is it parallel to the axis, as asked in the question? When is it moving in a northeasterly direction, if we were talking about bearings, and so on. So all sorts of things can be asked, and we need to be able to interpret the things that's been asked in terms of what does it mean for this velocity. So moving parallel to the I vector means that the j component is going to be 0. So parallel to I implies that 3t minus 5 is equal to 0. So that's a very simple equation then, and says that at that particular time t is equal to 5 over 3 seconds. Well, looking at the mark allocation for this question, the first part, very straightforward, M1, A1, so M1 for realizing you had to calculate by using Pythagoras' theorem, and A1 for getting the root 29. The second part of the question, 5 marks available here. The first, M1, A1, was for the equation for the acceleration, with a second A1 once the I plus 3j had been achieved. And then, as long as that was correct, a dependent M mark, so an M1 followed by an A1 to get the answer 2I plus 6j, giving you the 5 marks there. 4 marks for the final part of the question. M1, A1 for working out the velocity, so M1 and then a final A1 here for the actual velocity itself, and then M1 for realizing how to get the time when it was moving parallel to I, and a final A1 for the 5/3. Right, the final question I'm going to look at is from the January 2010 paper. This is one which is set in context. So we're looking at a ship which is moving with vectors given in the form of I and J, where I and J vectors are east and north respectively. So it says first of all that the ship is moving in a straight line with constant velocity. At time t, we have a position vector of s of s kilometers. When t is equal to 0, we're told that s is 9I minus 6j, so it's initially at a position 9I minus 6j, and then 4 seconds later at 4 hours later, I think it is, a position of 21I plus 10j. We're asked to calculate the speed, and then from that to work out the direction in which s is moving, giving the answer as a bearing, notice here, and also to show that s is given by an expression which is written in the question there. So 3 parts of the question. Just looking at the one at a time. The first one, the speed. Well, to get the speed, we need to calculate the velocity. So in the first part of the question, v is equal to the change in the displacement divided by the time. So that's simply comes from taking the 21I, which is the final position that we know, plus 10j, subtracting the initial position 9I minus 6j, and dividing that all by the time, which is 4. And if you do that, then it's quite straightforward to show that we get 3I plus 4j. That's the velocity, but we're asked for the speed at that time, so the speed is equal to square root of 3 squared plus 4 squared, of course 3, 4, 5 triangle, so this is 5, and we're talking about kilometers per hour. Part B of the question asks for the bearing that s is moving. So we know its speed now, we know its velocity 3I plus 4j. So it's worth drawing that as a diagram, because what we have here is 3 along the easterly axis, 4 on the northerly. Now we want a bearing so that the angle that we want to calculate is from north, so that the bearing is tan to the minus 1, 3 over 4, which turns out to be, to the nearest degree, 0.37 degrees, so 0.37 degrees as a bearing. In part C of the question, we're asked to show that s is given by this expression in the question, and that really involves us using the fact that the displacement at any time will be the initial displacement, let's call it r0, plus the velocity multiplied by time. So this is simply then a matter of taking the initial position, which was 9I plus minus 6j, and adding to that the velocity, which we know is 3I plus 4J multiplied by time. So the I component is 3t plus 9, and the j component is 4t minus 6, which is what we've been asked to show. Looking at the allocation of marks, 4 marks in the first part of the question. The first 2 marks were a method mark and an accuracy mark for getting the vector v, and then a method mark and accuracy mark for calculating its magnitude and getting the answer 5. The bearing likewise was marked M1 for using tangent inverse, and then A1 for the answer 037 degrees. And finally 2 marks in part C of the question, a method mark M1 and final accuracy mark if you've shown all the working. Remember that the answer's been given, so you do really need to write down some method to get that accuracy mark at the end. Well, that's the end of this lecture. There are other lectures in the series, and you can find out further information at the Further Mathematics Support Programme website, which is www.furthermaths.org.uk.